We live on a planet that appears calm, but that is an illusion. The Earth is a block of frantic heat locked behind a fragile crust. The clearest representation of that frenzy is the volcano. Most of us only think of the crater, the flowing lava, and the ash clouds. But what if I told you that what we see on the surface is only the tip of a massive iceberg? That beneath it are colossal, mysterious reservoirs, filled with molten material that science is only just beginning to touch. Some of these reservoirs lie deep beneath supervolcanoes, and we have no idea when they might wake up. For decades, we believed volcanoes were fueled by a simple, shallow magma chamber. But new findings, especially beneath supervolcanoes like Yellowstone, have revealed a complex, multi-tiered system lying hundreds of kilometers deep and many times wider than expected. It is a labyrinth of hot liquid, governed by rules that we don't fully understand yet. This isn't just a story about melted rock. It's a story about planetary dynamics, about how primordial energy travels to the surface through secret pathways. I'm David Loman, and you're watching Terra Mysteriosa. Today, we will embark on an adventurous journey deep into the Earth's interior, through the crust and into the mantle. We will discover how scientists are using seismic waves to see through our planet, and explain why understanding these deep, hidden magma reservoirs is key to predicting a global catastrophe, an event that could change human civilization forever. Part 1. The collapse of the traditional volcanic model. The old model, the most common model for a volcano, is the shallow magma chamber. We imagine a volcano like a bottle of soda, a vertical magma conduit connected to a pressure chamber lying about 5 to 15 kilometers deep. Magma accumulates there, gas and liquid pressure increases, and when the crust can no longer hold, it erupts. This model fits regular volcanoes. The problem is, when seismologists look at giant systems, particularly caldera volcanoes like Yellowstone or Toba, measurements of surface deformation and gravity changes indicate that too much material is moving. The volume of magma required to cause a supereruption is many times greater than what a shallow chamber can contain. The magma is hiding somewhere much deeper, and it must come from a huge source. Part 2. Earth's ultrasound, seismic tomography. To find this hidden reservoir, scientists must resort to seismic tomography, essentially a CT scan for the Earth. This technique is based on a fundamental principle. When an earthquake occurs, it emits seismic waves. These waves travel at different speeds through different materials. Seismic waves slow down significantly when passing through hot, molten material, liquid magma, and speed up when passing through cold, dense rock. By installing thousands of seismometers over a wide area, scientists collect data and map the wave speeds. This is the only way to create a three-dimensional image of the planet's interior. When they applied this technique beneath Yellowstone, the results changed everything. Part 3. The hidden core, the deep reservoir. The tomography data revealed the existence of an unprecedented two-tiered system. Not only is there the shallow magma chamber, 5 to 15 kilometers, but also a deep magma reservoir, lying at depths ranging from 20 kilometers to over 40 kilometers. This deep reservoir is estimated to hold enough magma to fill the Grand Canyon 11 times. The complicating factor: this material is not completely liquid, but a magmatic mush, where rock crystals are suspended in a molten solution. The actual liquid portion, magma, accounts for only about 2% to 15% of the total volume. This poses a major question. How can a reservoir that is not liquid enough to erupt power a supervolcano? Part 4. The energy supply channel from the deep mantle. The answer to the energy supply lies even deeper, in the mantle. Scientists suspect that the magma in the deep reservoir is not self-generated, but is continuously supplied by a mantle plume, a column of superheated rock rising from the core mantle boundary. Tomography has detected an ultra-hot zone extending for hundreds of kilometers beneath Yellowstone, acting as an energy highway supplying molten material to the system. Magma ascends, pauses in the deep reservoir for a rest and chemical processing, and then slowly pumps into the shallow chamber in preparation for an eruption. Part 5. The Mystery of Chemical Mixing. The biggest mystery about the enigma: magma from the deep reservoir and magma from the shallow chamber have distinctly different chemical compositions. Deep magma is often richer in magnesium, typical of the mantle, while shallow magma is richer in silica. This indicates that a complex chemical processing occurs as the magma ascends. The magma may accumulate volatile gases like water vapor and CO2 from the surrounding rock, or be contaminated with crustal rock. Understanding this chemical transformation, especially the accumulation of gases, is key to determining the timing and intensity of the next eruption. This is the most enigmatic part, as this chemical mixing process dictates whether the pressure is sufficient to fracture the crust. Part 6. The Latent Threat and Invisible Magma. The biggest mystery about the enigma: magma from the deep reservoir and magma from the shallow chamber have distinctly different chemical compositions. Deep magma is often richer in magnesium, typical of the mantle, while shallow magma is richer in silica. This indicates that a complex chemical processing occurs as the magma ascends. The magma may accumulate volatile gases like water vapor and CO2 from the surrounding rock, or be contaminated with crustal rock. Understanding this chemical transformation, especially the accumulation of gases, is key to determining the timing and intensity of the next eruption. This is the most enigmatic part, as this chemical mixing process dictates whether the pressure is sufficient to fracture the crust. Part 7. Comparison with other supervolcanoes. The existence of such colossal, deep magma reservoirs poses a far greater latent threat than we ever imagined. We are not just monitoring a bottle of soda, but a complex subterranean power plant. The most urgent question is, how long does it take for magma to accumulate in the deep reservoir, and what would trigger a large amount of liquid magma to ascend to the shallow chamber and cause an eruption? This is a problem of time dynamics. Could a distant large geological event, like a major earthquake, shake and activate the system? Scientists worry that the old model led us to underestimate the scale and preparation speed of supervolcanoes. Scientific summary and conclusion. The deep magma reservoir phenomenon is not unique. Scientists have found similar evidence beneath the Toba caldera in Indonesia, the cause of a mass extinction event about 75,000 years ago, and volcanic areas in the Andes Mountains. This suggests that this is a universal rule for large magma systems, where thermal and chemical stratification is essential to maintain the energy for a large-scale explosion. Each supervolcano is a time capsule holding secrets about Earth's harsh evolution. Decoding them helps us understand that devastation doesn't come from a simple shock, but from a subtle and slow process of energy accumulation. Seismic tomography technology is ushering in a new era, but the deeper we look, the greater the mystery becomes. Is the Earth hiding massive energy sources that we cannot control? Absolutely. Deciphering this magma labyrinth is not just a scientific achievement. It is a necessity for human survival, giving us more time to prepare for the inevitable event. Thank you for joining me on this deep dive into the Earth's core mysteries. Don't forget to like, share, and subscribe to Terra Mysteriosa so you don't miss our next journey. See you next time.